Quick. So welcome back, I guess. It's good to see all of you that are here today participating in Zoom, or if you're watching this on YouTube after the fact, I hope you're all doing well out there, and that everybody is safe and surrounded by loved ones in comfortable settings, even if we can't get out and do everything that we would otherwise like to do during these weeks. I know that I'm still feel like this whole thing is just an alternate reality. But we'll do the best we can, I guess, over the course of the next however long this takes, until we can be back on campus and in person again and not sheltering in place. So I sent out some information. If you're currently in my class, we're totally sort of rethinking the structure of the course to finish the semester. The biggest changes that we're thinking about making, and I mentioned these in a message, but let me actually pull them up so I can just talk through them one more time and make sure that everyone's on the same page. I'm just going to bring up our Canvas site on the screen here real quick. So by the way, one thing you'll notice about our Canvas site that has changed is that on the front page you'll see two is sort of dominated by these two video streams. One of them is this very Twitch stream that's streaming live right now. So even if you're not tuning in via Zoom and participating that way, you can also catch these streams live via this Twitch embed if you're not able to participate via Zoom. And then, as always, the videos that arise out of these presentations, so I'm recording this publicly facing video right now, this will be archived in our video playlist that now appears right here. All the previous content that was on the front of our Canvas page is still there, it's just underneath those two video links at this point. So let me go into the announcement that I posted. Sent. Did I put that in here? No, maybe, hold on. I think I put it in here, but it's probably buried so far down. Here we go. Okay. So here is here are the main sort of points of what we'll need to know sort of going forward. So how I'm at least initially planning on making some tweaks to the structure of the course just to adjust to a slightly compressed new reality. So let me make this window appropriate size so you can actually see what I'm talking about. Okay, so first thing to know is if you're participating live right now, if you're watching via Zoom, the virtual class meetings that we're having are going to take place at this time, so 2 o'clock on Monday and Wednesday. And this is my first time sort of streaming simultaneously to both Zoom and Twitch, so I know that there are some issues right now with the video quality in Zoom. So you may be able to click on my stream and get it to fill your whole screen, but if there's kind of a resolution issue, you may want to, well, we'll sort of see if that improves. I know that a ton of colleges and universities are using Zoom right now, so if there are some performance issues, I'll just have to apologize for those in advance, and we'll sort of see how things go. You may be able to get a higher resolution experience if you watch the Twitch feed that's on the front of Canvas rather than Zoom. The video is probably better streaming out via Twitch. The second thing to know is about due dates. What I'm going to be doing is lifting all of the due dates on the quizzes and exams that have been due up until this point. I'll just lift those to be out to the end of the semester, basically, and all the new quizzes that I post. I'm going to put due dates on them so that they show up correctly in your Canvas calendar, but I also recognize that if you can't get to them by the due date, if things are crazy, I will accept all late submissions without penalty at this point. So I'm definitely not going to be hawking due dates, with the exception of the due date at the end of the semester, May 11th. Definitely have to have everything in by then because we need to have final grades turned in at that point. Also, and this is probably the biggest, most important one to know about, is that I'm going to be counting your web work assignments now toward your topic mastery. So in our course, you're supposed to get these two different times you have to earn credit on a topic in order to get mastery. And before, those times all had to come on quizzes, exams, other things that are written down. But now I'll be letting you to substitute one of your web work. One of those can be covered by completion of the relevant web work assignment. So continuing to be active in web work is definitely going to be helpful now, not just to your engagement and enrichment and to your ability to practice the material of the course, but also it can count towards topic mastery now. So I'm hoping that that takes some of the pressure off. Additionally, my head's kind of in the way here on this one. The final exam will now no longer have the ability to decrease your overall grade relative to the bundle that you complete by the end of the semester. It can still increase your grade, it can still count towards topic mastery, but it can't bump you down. It can only bump you up or leave you where you're at. So that, I hope, takes some of the pressure off of the final exam when that comes along. Still gives you incentive to do well because you can still improve your grade, but your final exam cannot lower your grade relative to the bundle that you complete by the time the final exam comes along. So these are my initial thoughts for how to, sort of reorganize some of the course elements just to make the course more doable, I guess, between now and the end of the semester. But again, I'm going to be sort of continuing to reevaluate these things as we move forward to see if additional relaxation might be necessary to make sure that we all are able to get out of this course what you need to get out of this course at the end of the day. Why am I hearing myself in an echo here? Oh, I think it's because I just pulled up the Twitch stream. Okay, there we go. So before we get started with the new material of the day and dig into the math, let me just ask real quickly before we get going, are there questions, things that I need to sort of tackle, address about sort of the structure of the course before we get going into the mathematics today? Again, it's good to see the group of you here that are joining via Zoom. I hope that this sort of structure works okay for our class for the near future. But again, let me know if you have suggestions on ways that we can try and improve your experience, because I know probably every professor that you have right now is doing something a little bit different, which is good in some ways, but in other ways it can be challenging on the student end. So again, just let me know, and if there's anything I can do to try and tweak some things, I will definitely try to do that. So let's take a quick peek here at the agenda for today. So I've got kind of two main objectives that I want us to talk about today and do some problem solving around. The first one is going to be about finishing up our chapter on exponential and logarithmic functions, so chapter 3. When we last left off, we were getting towards we were turning the corner in chapter 3, where we had just sort of finished talking about the exponential functions portion of it, and we were just about to start talking about logarithms, which is just the opposite side of the coin. So that's what we're going to try to tackle today in the first half an hour or so that we're together. We'll talk about what is a logarithm, what can we do with logarithms, how do they help us to solve exponential equations, because logarithms are the inverses of exponentials. They let us undo whatever exponential functions do. We'll talk about some of the properties that logarithms have, and that will close out chapter 3. So if you're in the class this semester, this is the second half of what we're calling the C topics. So C4, C5, and C6 are the logarithm topics if you're keeping track on your topics list. And so after today, I'm going to be working on getting the next set of quizzes up for the C topics, so you can begin your work on that. And then we'll have exam 2. I'm not sure quite when yet. Probably push that out to next week or so, when exam 2 will be available for you to work on. And then we'll go from there. And in the second phase today, we'll do what we normally do on Mondays, which is do a bit on trigonometry as well. So our trigonometry workshop today, we'll talk about, first of all, the tangent function. So we spent a lot of time already talking about sine and cosine on the unit circle, as well as using right triangles. And now we'll dig in a little bit more to the tangent function, which is the ratio of the two. And then we'll begin our discussion that we won't probably be able to finish today about the inverses of trigonometric functions. So sine, cosine, and tangent also have, if we restrict their domain, they have inverses called the arc sine, arc cosine, and arc tangent. So we'll get our first exposure to what inverse trigonometry is, what it's about, but we're probably going to have to wait until either next class or next week to get much deeper into the inverse trigonometry puzzle. So that's kind of a sort of initial thought about what I'm hoping to be able to touch on over the next 45 minutes. Probably I'm going to end up needing to go a little faster on these video sessions, at least initially. We've got a little bit of catch up to do, so some of the topics might not have quite as much time to breathe as they otherwise do, for example, when we're meeting in class. But again, feel free to slow me down. If you're watching via Zoom, hit the raise hand button, which you can find in the participants menu, and it'll send me a little notification letting me know that your hand is up, and we can respond to questions that way as we move along through the video. So let's get started. And I spent some time thinking about whether we should start in this way, and I think I kind of like starting in this way because exponential functions have been in the news ever since the coronavirus pandemic has started to really sort of amp up in the news, and it all sort of hit us over the last 2 weeks, basically. And if you've been watching kind of, news sources and Twitter and those sorts of places, what you'll see are charts that look something like this. Let me zoom in on this a little bit so we can maybe look at it in some more detail. So this is a chart that I just found floating around on Twitter, where they took and they listed, here's how many confirmed cases of coronavirus there were in Italy at various dates, right? So the pandemic in Italy started a little bit sooner than it did here in the US, but then they put the US data alongside it also. And just sort of, the intention here is to try and show, hey, look, the US is roughly on the same trajectory that Italy was. I mean, you can kind of compare the two numbers across here and say, oh yeah, that kind of looks like, our numbers are growing about as rapidly as Italy's did about maybe 2 or 3 weeks, earlier. And so, that's fine. I think it can kind of, it's kind of a useful maybe comparison, a reference between the two countries. But it's, I think, more common, particularly in the news media, not to see this presented as raw numbers, but to see it presented as a graph. After all, this is, one of our ways that we communicate mathematically. And so, let me see if I go forward here, I can get, oh boy, what's happening? Hold on, I think I have to reset my iPad here real quick. Lovely. Okay. So what we might, sorry. I've got to adjust one more time here. Every time I reset the iPad on here, I've got to make one more adjustment to make sure you can all see what I'm seeing still. Nope, I think I need to make this bigger one more time. Sorry, I've got to make a little adjustment. I know you can all still see it. I'm just having to make a little tweak here. Okay. And so I can ask a question like the one that I have up here on the screen. A question like, well, according to the data that we're seeing, when do we predict that the U.S. will reach a level of 100,000 cases, right? And, we can see in the data just from Italy that the data in this chart at least don't even go that high on the Italy column. They only go up to about 20,000. So this is a classic sort of example where sort of a useful way to answer this question would be to come up with a mathematical model. But again, most of the time when we're seeing this information in the media, we're not seeing it as we're not seeing it as a table. We're seeing it as a chart. And this is an example of a chart that was in the Financial Times. I think this was just today that this was in the Financial Times. Let me get my head out of the way if I can. And so what you'll see in this chart is that the U.S. is this sort of, I think it's sort of pinkish curve. So they took the numbers, number of days since the 100th case, and they plotted a bunch of different countries. Here's the U.S.'s trajectory. But if you plot this data by yourself, I'm going to go into Desmos here real quick and just create a plot of this data. So I plotted these data points by myself in Desmos, and what I see is something that doesn't quite look the same as the chart in the Financial Times. So in the Financial Times, when you look at the US data, it's sort of going up, but it's going up at what looks like, if I just draw it in here, it looks an awful lot like we're on a trend line that is a straight line in this data. Right, if I sort of try to connect the dots a little bit here, it sort of looks like, I'm getting my head out of the way again, it sort of looks like the US is increasing at this, what looks like to me to be a linear function. But when I plot it in Desmos, it sure looks like not linear, right? It looks, in fact, like we're bending upwards, that there's a concave up quality to this data. And so the question I would ask us to think about is, why is there a difference? What is the difference? And maybe you can spot it if I sort of toggle back and forth here. What is the difference that you can see between the chart that I have of this data here in Desmos and the chart that appears in the Financial Times that's right here? Let me just pause on that for, 15, 20 seconds. If somebody can spot an important difference between this graph and that graph, there, what is the difference? They're supposed to be plotting the same data. Does anyone see why there's such a difference in the shape? There's the Desmos chart. Here's the graph from the Financial Times. What do you think? Yes, right. So you got it. The big difference between these two charts is that when you look at the vertical axis, which is over this shoulder, I guess, the vertical axis on the Financial Times is sort of looks funny, right? That the numbers are not going up in the same way that we usually expect them to, right? 200, 500, 1,000, 2,000. And you look on my Desmos chart, and they're going up in the way that we usually see, right? 1,000, 2,000, 3,000, 4,000, right? So that, in fact, is the important difference between these two charts. My Desmos chart is what we would call a linear scale. On my Desmos graph, I'm just going to sort of type this in here. On this graph, equal distances represent equal differences. In other words, the distance between, say, 3,000 and 2,000 is the same as the distance between 4,000 and 3,000, because both subtract to the same 1,000 number, right? So these tick marks on my vertical axis, let me just make them a little bigger so we can see them. The tick marks on my axis, is it going to let me do this? Yeah, there we go. There is an equal distance between 3,000 and 4,000 because that's a separation of 1,000 in difference when I subtract those two numbers. And that's the same as the distance between 3,000 and 2,000, between 2,000 and 1,000, because subtraction is the way that we're comparing the numbers that are on this vertical scale right here, and the horizontal scale for that matter as well. So then what's going on in this Financial Times graph over here? Let me just hide myself here real quickly. Just get my face out of the picture. Here we go. So what's going on here? Let's take as an example the difference between 1,000 and 2,000. Right? If this were my Desmos graph, the way that I would compare those two is I would subtract. Right? On my Desmos graph, I would do something like 2,000 minus 1,000 and find out that the difference there is a difference of 1,000. But then if that were the case, I would expect that the same plus 1,000 would get me to the next tick mark as well. And evidently, it doesn't, right? Because my next tick mark is not at 3,000, but at 5,000. So something different is going on here. We must be using a different kind of arithmetic to compare numbers on the vertical axis of this Financial Times graph. And the way to see that, let's use a couple of different. I'm going to measure this difference here between 1,000 and 10,000 and see if I can see how to do that. So again, we could subtract and call that a difference of 9,000, right? So if I subtract 10,000 minus 1,000. But then again, if that's what I did, I would expect that if I went up by the same distance again, I would add 9,000 and get to 19,000. But 19,000 is not, in fact, way up here, right? By the time I get way up here, I get all the way past 50,000. So there must be a different way that I'm comparing. So to give away the answer here, the different way that I'm using to compare numbers is not subtraction, but it's one level higher in the arithmetic hierarchy. Instead of using addition and subtraction, we're going to use multiplication and division to think about how numbers change, right? This is the theme of how exponential functions are different from linear functions, remember. So when we talked about what exponential functions were, how they were defined before spring break, the big difference was that we're no longer thinking about the y values changing by adding and subtracting multiples of a slope. Instead, we think of the y values for an exponential function as changing by multiplying by a number of powers of the base. Right? So rather than adding and subtracting, we're thinking multiplying and dividing. So here on this chart, what we would do is instead of comparing 1,000 and 10,000 by subtracting them, I want instead to think about comparing them by division. 10,000 divided by 1,000 is 10. And so how I'm going to think about this vertical axis is I'm going to think about equal distances being represented not by equal differences, but by equal ratios. In other words, numbers that are a factor of 10 apart from one another should all be the same amount of distance apart. And the way to see that that is actually happening is, once again, to hide my big head. Because this same distance of multiplication by 10 that separates these two figures, we can see that same distance also connecting 100 and 1,000 on this graph, right? Does that make sense? So the same amount of distance between 100 and 1,000, because those two numbers differ by a factor of 10, that same distance also gets me from 1,000 to 10,000, again, multiplying by 10. And if I did it one more time, it would take me from 10,000 up to 100,000. Because again, multiplication by 10. So that's how this scale on the axis works. The scale is what's often called a logarithmic scale. So this is our first clue to what logarithms actually are. Is there a way of kind of exchanging what we used to do with addition and subtraction for things that we now do with multiplication and division instead? So that's the sort of first main idea that we have here. And what this actually will do for us, if we think about why this graph over here might be a straight line, let's take and go back to our Desmos graph for just a minute. Our graph here wasn't a straight line, but it wasn't a straight line because my vertical axis here was a linear axis rather than a logarithmic axis. I think there's a way. I'm going to have to actually look this up real quick. I'm pretty sure Desmos will let us do a logarithmic scale. Let me just get this up here real quick. Sorry, kind of doing this on the fly a little bit today. Maybe there isn't an option to do that. Okay, well, instead, why don't we do this? If I just take two data points on my Desmos graph over here, let's say the data point that we have here at 0, 159. So let's take that as my first data point right here. on March 5th, 159 cases. Sorry, I'm drawing on the Financial Times graph again here. So 159 cases. And then let's take the 10 days later, I guess 9 days later, 2,836. And again, in the US data, that's right about here. 2,936. And let's focus in, 836, sorry. Let's focus in on those two data points for just a minute. And if I just think about those two data points in isolation, then here's what my graph's going to end up looking like. Let me zoom in on this one more time so we can see in as much detail as possible what's going on. So here would be the function model that we're kind of looking at, right? That I have this one point here at 0, 159. And then I had this second point out here at 9, 2,836. 2,836. And then again, on that Financial Times graph, it looked like we had a straight line that was connecting this, except that on my vertical axis was a log scale. And so on a log scale, remember, we're measuring everything by multiplication and division rather than by addition and subtraction. So the question I would ask us is, what's the slope of this line? And what does it mean? Because after all, slope is a quantity that we associate with linear functions and not with other types of function models. And so if we're asking a question about the slope of a line and my sort of scales on my axis are not linear scales anymore, then we should be prepared for slope to mean something different than it meant when we were just talking about linear functions in the first place. So what does it mean? So here's the clue. My x-axis is still measured on a linear scale, right? The number of days, day 0 and day 9, those are still measured on a linear scale on the Financial Times graph. And so we should measure the difference between 0 days and 9 days in the horizontal direction. We should measure that in the same way that we always did for linear functions, right? And the way we measured is by subtraction. And so I'll measure the horizontal separation between these 2 points by subtracting 9 minus 0. So 9 minus 0, that's 9. And so we would say that the difference between these two is an addition of 9 days, right? This data point is 9 days later than that data point. But on my log scale, I want to measure the difference between these two values in a different way. Between the value 159 and 2,836, there's a separation on the y-axis between those two numbers. But that separation on the y-axis, I want to measure 159, 2,836. I want to measure that not by subtraction, but by division instead. So on a log scale, we will measure by dividing instead of subtracting. And so I'll take out a calculator and I'll do 2,836 divided by 159. Let's see. I'm just going to type that into a calculator here, divided by 159. And that gives me about 17.8. I'm just going to sort of round that off. 17.8. And the way we're interpreting that 17.8 is that that is what I have to multiply 159 by in order to get 2856. Right, 2836, sorry. So 159 times 17.8 is 2836. And so how we could interpret this slope, so we have to be real careful about this. Let's keep the interpretation of this slope separate as far as how we talk about the horizontal change and how we talk about the vertical change. I'm going to kind of put that into a box up here. So how I would interpret this is over the course of a 9-day period, over a 9-day period, the number of cases in the U.S. increased by, and now here we have to be careful to communicate about multiplication and division rather than communicate by addition and subtraction, right? So rather than say it increased by 17.8, we have to say increased by multiplication by 17.8, right? 159 times 17.8 gives me 2836. And so we'll just add in some language that underscores that. Increased by a factor of 17.8. Or another way to say that, and we talked about this a lot when we first introduced exponential functions, is we could frame it as a percentage, right? If a quantity increases by a factor of 17.8, multiply that by 100, and we could say something like it increased by 1,780%, right? So that's how I can take those two changes and think about what they mean, how they inform what the slope of this line kind of tells me. What we haven't done, you'll notice, is we haven't gotten a single number for what the slope of this line is. And the reason for that is I don't want to divide 17.8 by 9, because division doesn't seem to be the right way to compare these two quantities that we arrived at in different ways. We had to subtract to get this plus 9, but we had to divide to get this 17.8. And so we can't compute a slope in the same way that we normally do. Instead, what we might do is just ask, if this is an exponential function, what is an equation for this exponential function? Right? And so here we'll take what we did just before spring break, and we can sort of plug all of that, all of what we did before spring break into this puzzle. So if I wanted an equation for this, my equation is going to look something like the template y equals a times b to the power x, right? If we think this is an exponential function, then this is the kind of equation that we will end up trying to fit to it. And we talked before the break about how this value, this a here that's out in front, this parameter, is a surrogate for the vertical intercept of my function. Just like the b in y equals mx plus b was the vertical intercept of that function. And so it just so happens that in my data we already have a vertical intercept identified, right? When x is 0, the value of y is 159. And so right away we know exactly what this value for a should be. It's my vertical intercept. Let's see, let me make a little bit of space over here. And so 159 is going to end up here, 159 times b to the power x. Okay, and so of course that leaves the question of what is b, right? B, remember, is the base of our exponential function, and it tells me what I'm multiplying my output variable, what I'm multiplying y by, every time that I multiply x by something. Or sorry, every time, I said that wrong. What do I multiply y by? Every time I increase x by 1. Every time I add 1 to x, what am I multiplying y by? And so to figure that out, what we could do is we could just plug in this second point here, 9, 28, 36. If I plug in those values for x and y, it'll give me a single equation that then I just have to solve for b. But what we'll notice is if I do that, let me just make a little room here. So if I plug in 28, 36 for y, 159 times b to the power 9, then the first thing I'm going to do to try to solve this equation is divide both sides by 159. But when I divide both sides by 159, take a look at the number that ends up popping out on the left side, 17.8. That's a number we've already seen, right? That's the number that I got when I divided this by this, right? And so another way to think about what this 17.8 and this 9 are telling me is that if it takes me 9 days to multiply my output by a factor of 17.8, then solving this equation for b is going to tell me what I have to multiply by in order to increase my number of days, not by 9, but by 1. And so I'll take a 9th root of both sides, 17.8 to the power 1/9, to figure out what we have here. Let me go over to our Desmos window. We'll just do that calculation, 159 to the power 1/9. And that gives me this value, about 1.7563. I'll just round it off to those 4 decimals. 1.7563. That's the 9th root of 17.8. So coming back to our chart over here, this can then be an interpretation of the slope of this line. 1.7563 is the base of my exponential function. 7563. And then I have 159 times 1.7563 to the power x. And again, what this number, 1.7563, is going to tell me is that every time I increase by 1, so every time I go forward by 1 day in this data, what am I doing to the y variable? I'm multiplying by 1.7563. Right? That's the meaning of the base of an exponential function. And of course, we can also frame it as a percentage increase. We could call it a 75.63% increase. And that's typically how this information would get conveyed in media reporting, right? The number of reported cases in the US, for each day, each single day that passed, the number of reported cases increased by 75.63%. So now we have an exponential function that's modeling this behavior. Let's superimpose that on top of the data points here and just verify that it kind of is matching what we're expecting to see. F of x equals 159 times 1.7563 to the power x. Okay, that's weird. Maybe something got screwed up here along the way. It certainly is matching my data right here at 0, 159, but it's not doing a good job once we get out. In particular, it's not going to the 0.9, 2836 like it was supposed to. Let's see, 2836, 159, 17.83. And then what did I do? It could be that I'm just having some rounding error here, 17.836. If I just use some more decimal places here, raise that to the power 1/9. Oh yeah, I must have mistyped something. My apologies. I missed a decimal place in my base. And of course, the fun thing about recording this on a video is you can see all of my mistakes, and then you get to see me fix them, and then they're all preserved for the record. So when I do this 9th root, I must have just written it down wrong here. I get something closer to 1.3773. So sorry, let me come back and fix that. 1.3773. And so for each day that passes, we're multiplying the number of reported cases by 1.3773, or, again, the way that it's usually reported in the media is that it's a 37.73% increase. Okay, so that's going to make this data it's going to make the model fit this data a whole lot better. There we go. So in my Desmos graph, now I can see, yeah, this function model actually is a much better fit than we had previously. So I want to return to the question we started with to motivate this study, which is, suppose I want to know how long it's going to take before we reach 100,000 cases. So I'd have to zoom pretty far out on this graph to figure that out. Let me actually sort of do it manually. If I zoom out my y-axis to show me out to, let's say, 120,000 or something like that. So, whoops, I think I had too many zeros. Here we go. And so the question is, at what point are we going to get to the 100,000 cases mark, right? So that would be this point right here, which again, Desmos is a friendly ghost. It can give me approximate coordinates for this point. It shows me that at about the 20-day mark, so March 25th, so that's Wednesday, is when, according to this data that we started with, we would expect to see 100,000 reported U.S. cases. But the question of the day is, how do we arrive at an answer like that using algebra rather than using a numerical approximation? What is the algebra that goes into reversing an exponential function, solving an exponential function for a value of its output? So here's what I mean. Oh boy, I think I have to quickly reset the old iPad one more time and hopefully not screw everything up in the process. Okay, so I'm going to have to solve an equation. So let's start with my function. I'm writing it down here. You can't quite see it, but you'll see it in a second. So we have this function f of x equals 159 times 1.3773 to the power x, right? And I want to know at what point this function is going to take the output value, the y value, of 100,000. 100,000 equals 159 times 1.3773 to the power x. So that's the ultimate kind of equation that we're going to have to wrestle with solving here. And if you follow me over into the activities from this section, section 3.4 of the text, we'll see some equations that have this flavor, this kind of flavor to them. So here is activity 3.4.2. It has some equations, and I would say equations like the one in part C here kind of have that flavor, where the variable that we're solving for, x in this case, is stuck up here in an exponent. And so the big question that we need, and what logarithms are going to answer for us, is how do we rescue a variable or an exponent from out of an exponent? So when the thing that you want to solve for is trapped up in an exponent, how do we rescue it? How do we get it down out of that exponent so that it can be by itself and we can figure out what its value is? So let's look at just sort of the basic principle behind how to do this. And the basic principle is the following. What we do in order to solve such an equation is we just have to give this inverse function, the inverse function of an exponential function, we just have to give it a name. And the name that we give it is we give it a name logarithm. So if I have an equation b to the power x is equal to y, right? And I want to turn this equation around to get the x by itself instead of the y by itself, then what I'm trying to do is just reverse the roles of y and x. In other words, I'm just trying to find out what is the inverse function to the function f of x equals b to the power x. How do I undo what the function b to the x is doing to the left-hand side of this expression? And the inverse function is called a logarithm, and that's all that we need to know about what logs are. They're the opposite of exponentials. They're the inverse functions of exponentials. And so anytime x is related to y by an x being in the exponent and a y being the value of that power, then when we reverse the roles of x and y, we exchange an exponential expression on the left-hand side for a logarithmic expression. We read this as the base b logarithm of the value y. Okay, so let's talk through that one more time. If y is the xth power of b, then conversely, x is the base b logarithm of y. That's all. These two equations are both simultaneously true. Right? In this equation, y is the subject. In this equation, x is the subject. But any exponential equation, we can turn around into a logarithmic equation and vice versa, because that is the very definition of what logarithm means. So this is something not to, it's something to groove into your brain. I think this little animation does it better than anything else that I know of, right? But not to overthink. People get wrapped around the axle about logarithms all the time because it's a big scary concept that people don't encounter until a pre-calculus class, when really it is just an answer to the question, how many powers of b does it take to make y? That's really what this is saying, right? The base b log of y, x, is the number of powers of b that it takes to make that value. So let's look at maybe a basic example from this activity. If I take this expression right here, the base 10 logarithm of, this is 1 million, right here. If the base 10 logarithm of a million is equal to t, then the way to figure out what the base 10 logarithm of a million actually is to think about what it means, to use that exchange, that interchange, to turn that statement around. Let me zoom in on this a little bit so you can see what we're writing. I just want to turn this expression around. And I do that by exchanging the role of the value inside of my logarithm function and the value that we get on the right-hand side here. I just want to trade places. Take my 1 million and my t and just swap them. And when I do that, my base 10 logarithm function gets replaced by its inverse, and its inverse is just 10 raised to that power. So in other words, when I rewrite this equation, what it looks like is 10 raised to the power t is equal to 1 million. Right? So all I've done here is I've just done the same do-si-do that we did over here. I can turn any logarithmic equation into an equivalent exponential equation by reversing the roles of the argument to the log function and the value of that logarithm. And when I reverse those roles, the log changes into the exponential function with that base. So the base 10 log of a million is equal to x if and only if 10 raised to the x power is equal to a million. So the base 10 log of a million is the answer to the question, how many powers of 10 do I need to make a million? And because a million is a friendly relative of the number 10, we can sort of think this through without using a calculator, right? How many powers of 10 does it take to make a million? Well, 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000, and so forth. So the exponent on that 10 just counts the number of zeros that we're placing on the end of that power of 10. And so we can do this one by inspection. A million has 6 zeros in it. 10 to the sixth power is equal to a million. And because 10 to the sixth power is equal to a million, when I trade places between the 6 and the million again, my function changes back into a logarithm. But now we've discovered the value of this t. We've discovered that it should be equal to 6. So that is how we use the definition of a logarithm to evaluate logarithmic expressions. Let's do another one together, if you like. I'm going to switch over to this wonderful app called Graspable Math to do this. So let's do another power of 10 example. Let's see. How about this? So you can't see it quite yet. Whoops. Something didn't quite work right there. Let me fix this. 10. Okay. All right. So here is another example. Suppose that I want to know what is the base 10 log of the number 0.001, right? So often when you get a question like this, you don't have an equals x or something on the other side, but I think it really helps to write that because then this is going to remind us that the way to solve this problem is just to convert from a logarithmic expression into an exponential expression instead. So the role of my x here is my unknown value, the value of my logarithm, and the role of y here is being played by the thing that's on the other side of the equation, which is inside of my log here, 0.001. So if I want to know what is the base 10 log of 0.001, I'm really asking how many powers of 10 does it take to make 0.001. So in other words, we can just change that equation into its exponential form. instead of its logarithmic form. And just think about how many powers of 10 do I need in order to make this happen. And so we can try some stuff, but again, because 0.001 is less than 10, in fact, it's even less than 1, right? The powers that we are going to have to plug in for this x here are going to be negative powers rather than positive powers. So another way to think about this is to maybe take this 0.001 over here and turn it into a fraction instead. So as a fraction, 0.001 is 1 over 1,000. So another way to think about this equation is it's really 10 to the power x equals 1 over 1,000, right? And so, let me move this. There we go. And so if I then bring my logarithm over here, x is the base 10 log of 1 over 1,000. But here's maybe another way to think about how we might solve this. What would I get if I took the reciprocal of both sides of this equation? Right? If I raised both sides to the power -1, I would get 1,000 to the -1 on the right-hand side. That is what 1 over 1,000 means, right? But then this gives me a clue as to how I might get rid of this -1 so I can think about bigger numbers instead of smaller ones. If I take this -1 and raise both sides to the -1 power, now, whoops, that's not what I meant. Oh, I see. X times -1. Yes, that's in fact what I mean there. 10 to the -x equals 1,000. So this is kind of interesting, right? What we now have is a way of thinking about powers of 10 that are larger than 1 rather than smaller than 1. Well, what is 1,000? 1,000 is how many powers of 10? It's the number of zeros that I have here, right? So 1,000 is 10 to the power 3. So, oops. What I want here, I'll just sort of put that back in. So now I've made the observation that my right-hand side, is 10 to the power 3. And when I make that observation, yeah, let's sort of, why don't I just get rid of that last one. Here we go. Now something jumps out at me, right? Both sides of this equation are 10 to some power, right? And every exponential function, as we know, the graph of every exponential function passes the horizontal line test. And what that means is that every exponential function is 1 to 1, meaning that if two exponential functions, if two output values from an exponential function are the same, that must have meant that the input values from that function were the same. There's no way for an exponential function to take two different inputs and give me the same output. And therefore, what I have here is 10 raised to some power being equal to 10 raised to some other power. And since exponential functions are 1 to 1, what that allows me to do is just to get rid of, that's not quite what I wanted. It allows me to get rid of the tens in this expression. And so what I'll get when I cross out the tens is I'll get -x on the left-hand side, and I'll get 3 on the right-hand side. So this is kind of a dream case for solving one of these kinds of equations, because now, how do I finish? I just have to get rid of this minus sign that's out in front of the x just by dividing by -1. I know there's a way to do that here. No, that's not what I meant. How do I divide by -1? I guess it probably wanted me to write -1 times x or something. -1 times x. Right? That is what -x means. And now if I divide by -1 on both sides, just do that arithmetic, I get my answer. And so running that all the way back to the beginning, 10 to the -x equals 10 to the power 3. The reason we were there was that we were looking for the base 10 log of 1,000. Not 1,000, actually. We were looking for the base 10 log of 1 over 1,000. So again, I could take this and write it as, sorry, I don't want to confuse things here. So let's just go through the steps that we did to get to x equals -3 at the end of the day here. we started with the question, what is the base 10 log of 0.001? And we figured that out by changing my base 10 log into an exponential expression, 10 to the power x equals 0.001. And then to make our lives a little bit easier, we took a reciprocal on both sides to turn this into 10 to the power minus x equals 1,000. And then we solved that logarithm problem. So we turned it into 10 to the minus x equals 1,000 by taking the reciprocal on both sides. Right? And then once we figured out that this x, this minus x rather, should have been the base 10 log of 1,000, the base 10 log of 1,000 being 3, then we just had to multiply both sides by -1 to find that x is equal to -3. So that little do-si-do that we do here to turn an exponential equation into a logarithmic and vice versa, this is the most important thing I want you to get out of today's class, right? If you remember nothing else about logarithms from today, it should be that they are nothing more than what we get when we transpose the input and output of an exponential function to find its inverse. The inverse of the base b exponential function is the base b logarithmic function. So let's use that to come back to our main question for today, which was about the data from the U.S. Coronavirus data that we sort of started from today. And so the question we were asking was, when do we expect the U.S. to reach 100,000 cases? So using this data that came out of the function that we started with here, how do we figure that out? So to figure that out, the first thing we need to do is get my right-hand side to be just an exponential, just the base raised to the power x. So to do that, I'm going to divide both sides by 159. So I divide by 159 on both sides. I'm going to get a right-hand side, which is just 1.3773 to the power x. And I'm going to get on my left-hand side 100,000 divided by 159. That's 628.93. Okay. And so now I have what looks like an exponential equation. I have an exponential expression, 1.3773 to the power x, and I have a number, 628.93, on the other side. I'm going to write that on the right side here. 628.93. But now the issue is, if I do my little do-si-do and replace my exponential expression with a logarithmic expression, then the base of that logarithmic expression is going to be the same as the base of my exponential function, that 1.3773. So let's do that little do-si-do, trade places with these, and turn this into a log instead. Log base 1.3773. Right? And so what I'm going to get is an expression that looks like this. Log with a base of 1.3773 applied to the number 628.93 is going to be equal to my unknown x. And so while this is correct, it's also not particularly useful yet. Sorry, I'm a little off the screen. So this is a correct expression right here for how many years it's going to take the U.S. to reach these 100,000 cases. The problem is that we can't go into a calculator and ask for a base 1.3773 logarithm. We need to figure out a way to make this something that a calculator can evaluate. Because the fact is, if you sort of pull out a calculator, just get an image of a scientific calculator up here on the screen. Yeah, here's one. Sorry, give me one more click here. There we go. So here's a typical scientific calculator, a really basic one, right? And if we want to know how to take a logarithm on one of these devices, we're going to have to find buttons for logarithm. Well, issue is there's only two buttons for a logarithm on a typical scientific calculator. One of them is right here. It's called the ln, or what's called the natural logarithm button. And the other one is right there. It's a little higher. There we go. It's called log, right? So there are two buttons on a typical calculator that perform logarithms, an log and an ln. And so what do those two things mean? Well, on a calculator, when you see the button that's called log, what that stands for is it stands for a logarithm with a base of 10, like the examples that we had been talking about earlier. The button ln on a calculator stands for a logarithm with a base of e, that natural number, 2.71828 and so forth that we were talking about just before spring break, right? So those are the only two bases that calculators know how to compute logarithms in. And so if we want to know a logarithm with a different base, we're going to need to know more about the properties of logarithms. How do I transform this logarithm with a base that I don't know into a logarithm with a base that a calculator does know, so that we can then use that to do our computation. So what I want to pivot to now, this is going to wrap up our content on logarithms for right now. We're going to pivot to talk about some of the properties, the algebraic properties that logarithms have. And how do we use those algebraic properties to help us to figure out logarithms with different bases and so forth. So this is how we're going to sort of round things out for today. So there are sort of four main properties of logarithms that we're going to care about at the end of the day. And each one of them comes from a corresponding property that exponents have. So for example, the first property we'll talk about is the product property. We know for exponents that if I multiply two exponential expressions with the same base, so a to the power n times a to the power m, if I multiply those two things together, that I can just add the exponents, right? So just rewind that tape for a second, right? Multiply together two exponential expressions with the same base, and the result is we can just add the exponents. Multiply powers, add exponents. Well, because logarithms are nothing more than the inverses of exponential functions, right? What we can do is exactly the opposite, right? When I add exponents, it's the same as multiplying powers. So when I add inside of a logarithm, it's the same as multiplying on the outside of a logarithm, right? So when I add exponents, I multiply powers, which is why when I add logarithms, I multiply what's on the inside, right? So anytime I see multiplication happening inside of a log, that's the same as addition happening on the outside of the log. And these are both reflections of the same property that we already know of exponents. So we haven't really seen a use of this just yet, but we have already seen today a use of this second property that I want to talk about. This is the power of powers property. Let's talk about this one real briefly. We know for exponentials, when we take a power of a power, so in this example, a to the n power, raised then to the mth power, what do we do with those exponents? We can multiply them. So this m power applied to the a to the n on the inside becomes a to the n times m. Right, so a power of a power turns into multiplication of the exponents. And for that same reason, when I have a power going on inside of a logarithm, like x to the power y here inside of a logarithm, that power can become multiplication on the outside. So the log of a power is a multiple of the log. An exponent on the inside of a log can be brought out as a multiple on the outside. So where we already saw this in use today was when we were talking about the log of 0.001. That was the log of 1 over 1,000, or 1,000 to the power minus 1. So let me move this down into frame here, right? So earlier when we were working with this expression and trying to simplify it, right, we were able to transform the log of the reciprocal of 1,000 into the opposite of the log of 1,000. those two are equivalent algebraic expressions. So anytime I have a power on the inside of a log, we can transform it so that it becomes a multiple. We can pull out the exponent, and it turns it into a power. Okay, well, what's good for the goose is good for the gander, as they say. And so anything that we say about how logarithms deal with multiplication, we can turn that around and get a corresponding statement for what logarithms do with division instead. We should just do the opposite. So we know from properties of exponents that if I divide two powers of the same base, so a to the n over a to the m, I can change those exponents by subtracting. Right? A to the n over a to the m is a to the n minus m. So exponentials turn division into subtraction. Subtraction of exponents is division of powers. And for that same reason, anytime I have division on the inside of a log, I can turn that into, whoops, let me undo that because it sort of runs off the screen. I can turn that into subtraction on the outside of a log. So, sorry, let me get that into the frame here. Real quick, there we go. So division on the inside of a log turns into subtraction on the outside of a log. By the way, one of the ways that we could think about that, and this is going to let us also learn one more important property of logarithms here in a minute, right? Let's return to this problem that we had before, right? Log of the reciprocal of 1,000. Well, if I rewrite that as log of 0.001, let me rewrite that too. Whoops. Yeah, I know it's -3. Hold on. I want to rewrite that as a fraction. So 1,000, there we go, 1 over 1,000. If I write that as 1 over 1,000, then I could use this subtraction property to write this as log of 1 minus log of 1,000, right? But then we already said that this was just equal to minus the log of 1,000. And it's almost as if this log of 1 wasn't even there. Well, why might that be the case? Because the log of 1 is equal to 0. Why should the log of 1 be equal to 0? Let's go back a step here. The log of 1 is equal to 0 because, let me add in an expression here. If I want to know what the log of 1 is, I'll just sort of write it as an unknown x, like this, right? And then if I want to know what the log of 1 is, I'm really asking how many powers of whatever my base is, in this case my base is 10, how many powers of 10 does it take to make 1? 10 to what power gives me 1? But we know the answer to that, don't we? Right? How do we get 1 out of a power? We just use an exponent equal to 0. Okay. So 10 to the 0 power is how we get 1. And so the implication for that is that the base 10 log, in fact, the base anything log of the number 1 is in fact just equal to 0. So log of 1 is equal to 0, and that is why the log of 1 over 1,000 was minus the log of 1,000. It's the same division property combined with the fact that the base, any base log of the number 1 is equal to 0. Okay, and now the formula that we came here for in the first place. The formula we came here for is called the change of base formula, and it's called that because, not surprisingly, it allows us to change the base of a logarithm so that, for example, we can evaluate a logarithm using a calculator. So here's how the change of base formula works. It works here as a way of reminding us that an exponential and a logarithm are inverse functions to one another. So if I take a base and I raise it to the x power, but then I also take the base b log of that thing, okay, that the results just cancel one another out and I'm left with x, right? It's because, by definition, logarithm and exponential are inverse to one another, right? But then remember what we said about exponential functions being one-to-one. Exponential functions are because exponential functions are one-to-one, we can say for sure that, actually, hold on, how do I want this? What do I mean here? Oh, right. So if I take the if I rearrange this as a logarithmic equation, what I get is the equation that I see underneath here, that the log with a base of a, no, what I want is I want to take the base b log of both sides of this equation. And I get something that looks like this. But then if I rearrange the factors in this equation that's down here, I can get, I'm forgetting what the trick is here. I forget how to rearrange this equation. Sorry, I'm kind of doing this on the fly today. I do want to show this derivation maybe at another time. But the upshot of this, let me just write in the final conclusion here, is that the log base b of x is equal to the log base a of x divided by log base a of b. So what we end up with when I rearrange this equation, and again, apologies, I'm having a brain freeze right now. When I rearrange this equation, I get this result that's called the change of base formula. And what the change of base formula is telling us is that if I want to take a log to any base that I like, log base b, I can do that by transforming it into a base a log instead. And as a base a log, we're just going to take the base a log of the same x and divide it by the base a log of b. So to return to our the motivating question for the day today, how many days would we expect to see the number of cases hit 100,000? This expression, log base 1.3773 of 628.93, the role of b here is being played by 1.3773, and the role of x is being played by 628.93. And so if I want to use this change of base formula, I can use that by evaluating the base 1.3773 logarithm of 628.93. I can replace that by the log of any base that I like to. So I'm just going to write an a down here. Log base a of 628.93. And then divide that by the base a. Again, same a, so the only requirement here is that we use the same base in the numerator as I use in the denominator of this formula, the base a log of 1.3773. So that is the magic of the change of base formula. Change of base. Right? And the reason that it helps is that now I can choose to either set a equal to 10 or set a equal to e. It completely does not matter to the final answer which one of those two that we pick, but either of those are logs that I can ask a calculator to perform for me. So let's just for fun, let's choose e for my base, log base e, right? And if I choose log base e, that goes by a different name on your calculator. It's called a natural logarithm, ln, logarithm natural, ln, right? And so now, this tells me that all I have to do is pick up a calculator and just type in the natural log of 628.93 divided by the natural log of 1.3773. And I'm just going to do that for kicks here on a Desmos calculator. So we'll do ln of 628.93 divided by ln of 1.3773. And there is my answer, 20.12969, right? Which, if you remember, that looks exactly like the decimal that Desmos gave me in its approximation for where the intersection of these two curves are, right? My exponential function that models the cases over time and the number 100,000. Right? So the important bit here was our use of the change of base formula at the end. This is the property of logarithms that we didn't have when we first started algebraically solving this thing. But it's what we then use to get down to our final answer as an approximation using a calculator. 20.13 days. And again, since the units here were days after March 5th, that would correspond to March 25th. So we'll watch the news reports this week, and we'll have our next class meeting on Wednesday. We're going to pick up where I'm leaving off right now. So we've talked about the log properties. We're going to move forward into the trigonometry piece on Wednesday's class meeting. I hope you all stay safe, stay comfortable. Be watching for more announcements from me via Canvas, as well as pushed out to your email. What work should we be doing this week, you ask? I would say start with the web work for right now. So you have web work assignments to work on. What the material we talked about today can be found in the web works for C4, C5, and C6, so the logarithms and properties thereof. And so I would start by working on those. Remember, now your web work can count not just toward your engagement and enrichment credit, but it also counts toward topic mastery. So if you master the web work assignments on those, you'll get your first check mark toward the mastery of those C topics. And then I will be posting a quiz on this material probably tomorrow. At this point, I'll start posting some C quizzes, and then you'll have some C quizzes to work on as well. And those should be the focuses right now. Any other questions from participants in the Zoom chat right now before we wrap up today's video session? Thanks for joining me, by the way. And again, if you have other questions or hints and tips about the technology that I'm using here, please feel free to forward those to me. Either drop me a Canvas message, send me an email, ask me during one of our class sessions in Zoom. I'm also holding Zoom office hours on Monday and Wednesday from 12 to 2, so for the 2-hour period before our virtual class meeting. Feel free to drop by my Zoom chat, and we can talk, one-on-one. We can do some work in small groups. And so forth. So for now, I would say start by prioritizing the web work, and then when the quizzes go up in Canvas, you'll get a little notification that the quizzes are available to work on as well. I think I'll sort of tentatively set sort of a suggested due date. Remember, all of our due dates are suggested from now on, but the suggested due date for the work on the C topic quizzes is going to be Monday of next week. So that would be whatever that Monday, April, I think it's April 1st, I want to say. So that'll be the sort of tentative, March 30th will be the tentative when you should be thinking about wrapping up your work on the C quizzes once the C quizzes get posted. So again, thanks for joining the session today, and I hope I'll see you again on Wednesday and later in the week.